Okay, so this is a course on algorithms. In case somebody joined today, so you would have seen algorithms in your high school day-to-day life, adding numbers, multiplying matrices, computing GCD of two numbers, taking square root of a number. Many things you would have seen throughout your high school and maybe even in the college days. So in this course, we are going to take a little systematic attempt at studying these algorithms. In particular, we care about why those algorithms are correct, because for example, you would have seen this Euclid's algorithm to compute GCD of two numbers, which just works by subtracting something, and you do these repeated subtractions, and then you would want to know why is the algorithm correct, right? So we would be worrying about correctness, how efficient algorithm is compared to a naive algorithm which lists out all the divisors of a number and then picks the largest, for example. Okay, so in terms of efficiency, we saw last time that there could be a big difference between even n square versus n log n for large values of n. For example, n square algorithm would take something like 315 years, whereas this will take some 40 seconds, right? For n in the order of 10 power 10 on a machine which can execute 10 power 10 instructions per second. Okay, so we care about efficiency, and I did mention that we may not be lucky all the time to get an n log n or linear time algorithm. Later on, we will see problems where we have to live with even exponential time algorithms where n is at the exponent, and but the point is to design faster and faster algorithms. So we look, then that took us this problem of sorting. Okay, we also saw binary search. So this is all last time, right? I illustrated it by, I think of a number and you're supposed to guess that number by asking me yes or no questions. And if my range of the numbers is between 1 and n, then what is the minimum number of questions? What is the strategy you will adopt? And we saw that, again, I'll do some formal analysis today, but roughly, this many comparisons or questions is what you needed to guess my number. And so this is not just a puzzle, but for example, if you have a sorted array, you can apply the same strategy, that if you have a huge array arranged in increasing order and you want to query whether an element is in the array or not, you go to the middle of the element, and depending on the answer to the comparison you get, you can throw away half the elements, and that has a very similar flavor as the strategy you had for guessing the number. And so you can search for a number in a list of size n if the array is sorted in log n time. That took us to this problem of how do you sort, right? That given some sequence of numbers, you want to arrange it in increasing order or decreasing order. So we saw a couple of algorithms. One algorithm was repeatedly find max. Right, take your list, find the maximum, put it at the last location, swap it with where it came from, and swap the last element with where this element came from, and then find the max of the first n minus 1 array, and keep going, and at the end of it you will have your array sorted. And this algorithm, the number of comparisons performed was something like n minus 1 plus n minus 2 1, and so this we estimated to be n square by 2. The other algorithm I described was repeatedly insert the next element, the ith element, let's say, into the sorted array of the first I minus 1 elements to make the first I element sorted. Right. So, for example, if this is your array on n elements, then I know that this single element is sorted. So, somehow I insert this element into this sorted array, and at any point of time, if I have these I elements sorted, I take the I plus first elements. So, let me put in quotes insert. How do I insert? We will come to that. Somehow find the correct location for this element in this sorted array and put it in that correct location, so that this entire array gets sorted, and at the end of it you will have the whole array sorted. Okay. So, these are a couple of algorithms we saw, and how do you insert the ith element into this array? Since this is already sorted, you can apply binary search taking log I many comparisons. So, the overall number of comparisons would be summation log I going from 2 to n, which we saw was at most n log n. However, I did point out something about this algorithm, that it is really not an n log n algorithm, right? Does anyone remember what the issue was? Why was it not just an n log n algorithm? Is the question clear? No, you can do binary search, right? Yeah, the shifting, exactly. So, the number, so there are two operations happening here. One is the number of comparisons. So, I take the ith element, compare it, that number of comparisons would be log I, because I am doing binary search. But when I insert the element in an appropriate location, I may have to shift everybody. So, that in the worst case could be I many operations. So, it will be summation I going from 1 to n minus or 2 to n, which will be n square. Okay. So, this brings us this notion, just want to draw your attention that when you want to analyze an algorithm, you want to look at all operations. Okay. So, if you care only about comparisons, yes, binary insertion sort, this is called, so this is called, by the way, selection sort, and this is called insertion sort. These are simple sorting algorithms. For example, if you have a, if you're playing a game of cards and you want to organize them in some order, typically insertion sort is what you will apply. You take the new card, insert it in its correct position, right? But both of them take n square time, where time here means I am talking about number of comparisons and the number of swaps or moves. These are the typical operations in this sorting algorithms. Okay. So the last time the idea was to tell you a bunch of things about the importance of algorithms. This tells you why you need to care about efficient algorithms, just some simple binary search, couple of sorting algorithms, how do you analyze them, and so on and so forth. So, let's get to some terms I will be using, because I think I will subconsciously use them. Let me mention all of them, and then we will get on to other problems and algorithms. So, right, this also brings us this notion of data structures, right. So, that is one of the things we will look at in this course. Which is, how do I organize a set of data so that certain operations on them can be efficiently supported. Okay. So, for example, I give you a list of elements, and the only operation I care about is, given a query element, is it in the array or not, is it in the set or not. Then the best way is to just keep the array sorted, and that is a data structure where you can search in logarithmic time. But if I also want to occasionally insert an element, then we know that the sorted array is not good enough to support in logarithmic time, because insertion can cause a lot of swaps, resulting in even in linear time. Okay. So, you need to come up with some better data structures. So, we will get to these things later. So, typically data structures is, algorithms use often repeated queries on something. So, you need to think about, how do I organize so that these queries can be supported efficiently. That takes us to the realm of data structures. Okay. So, these are some of the things we will be looking at in the course. Okay. So, let me just make some So, two basic data structures, let me say, because I might use them, are arrays and linked lists. Okay. So, you can think of it like some sort of a axiomatic kind of data structures, very at the atomic level. So, an array, we already talked about it, is just a sequence, a set, a sequence of contiguous cells. If you can visualize the whole computer as organized into a big array of cells. Okay. So, each cell can take some value, and when I say array, means that it is a set of contiguous set of locations. So, that I can go and say, give me the 5th element, 10th element, or 15th element. I can index, right, can index, which means access a location in constant time. Again, I need to tell you what time means, I will come to that later. The linked list, on the other hand, so have you guys seen linked list? Maybe if you have written some programs, how many people have seen it? Okay, good, about 50% of them. So, linked list, think of it as, you have not necessarily contiguous set of locations, So, because maybe your program is using some cells, then suddenly you need something which is not necessarily the next location in your computer. So, it is going to come from somewhere, but these are connected through some what are called pointers, which are, you can essentially an address. Okay. So, there will be a start or begin or first element, and then who is next to this guy will store it. There is a pointer which stores saying, so this guy is next to me. Okay. Who is next to this is, there is an address which will tell you who is next to me, so on. So, each of the cells now will have at least two values, a value which if you are trying to sort some numbers or something. In addition, it will store an address which points to who is next to it. Okay. So, I mean, a simple way is, suppose you are all sitting in this classroom, and I can say, an array would be, I can say the first bench would be 1, 2, 3, 4, 5, 6, 7, and then the next bench and the next bench and next bench. I have organized it that way. So, now if I want to know, hey, that I want the 27th person to speak to me, it is very easy to know, because you know how many people are sitting in the first row, how many are second row, and then you know where the 27th element is, and that person can speak, right. However, in a linked list, who is 27 is not clear. So, what I will tell you is, I will point out to the first person and say, you are the first, and I will give him or her who is the next person. Okay. So, that person may be sitting in the last bench, and that person will have an address to who is the next, and so on and so forth. So, if I want to know who is the 57th guy, how do I know? How can I find out? Yeah, I have to go to the first guy and ask who is next, and then go to that person and ask who is next, and have a counter which runs it. And the moment I get a 57, so here I can't access the ith element in instant time, right? So then what is the advantage? Why do I care about linked list? Well, insertion is easier in a linked list. So suppose I want to insert somebody between 23rd and 24th element. How do I do it? I go to the 23rd element and say, who are you storing as next? Oh, not that guy anymore. This new person who has come is the next element, and whoever that guy was storing will be stored by as a next element for this. End of the story, right? That's it. However, in the array situation, you are all sitting together and I want to insert somebody between 23rd and 24th. I have to move everybody. Let's say you have enough space for one chair, one person. Then I have to make the 24th guy sit next to 23rd and move everybody down. Okay. So, these are some basic data structures, and we will build more as and when I need it. Okay. So, now let us come back to the insertion sort algorithm. Yeah. So say our sorting process is done. Now we have the complete linked list. Can we make it into an array now? So that accessing a location is easy. Yeah, okay. So I'm just coming to that. So okay. Let me ask my question and then maybe things will be clear. So I'm saying let's come back to the insertion sort algorithm where we said I have this portion sorted. Now I want to insert the next element. How do I insert it? How much time does it take, right? So we saw that we can do binary search if I keep it in an array, which will take log n time, but then the switching of elements will take some linear time. Maybe if I don't keep it as an array and keep it as a sorted linked list, does that help to insert faster? Yes, no? Sorry? Your voice was breaking. Yeah, so anyway, the point is you can't search, you can't apply binary search now, because what is the first step in binary search? Go to the middle element and compare, whereas in a linked list I can't do it. Okay. So, a sorted array has an advantage that you can search, but sorted linked list you cannot search, though you can insert. If you know the position, you can insert fast. So, neither of these data structure gives me a way to insert and search in logarithmic time. So, you need more involved data structures. We will get to that later. Okay. So, I just want to throw at you that the power of data structures, why you need them, because if I want to do insert and search in logarithmic time, neither sorted array works nor sorted linked list works. You need to build more complex data structures. We will get to that later. Okay. So, that is just to throw you why you need efficient data structures. Okay, good. So, let us get back to when I design algorithms, what do I mean by, for example, time here, right? So, for most of our algorithms, we will be using what is called a RAM model. These are some boring things which I want to say it so that, because subconsciously I will be using it, you will be clear what. So, what it means is that when I am designing an algorithm, I ask my computer for a set of locations to store my data. So, let us say I organize it the way I want it, but I have the data stored here, and my program is executed or the algorithm is executed step by step, where I assume I can access any location here in constant time. If it's just an array, of course, you might change the data array into something else and store something else, and may store in a different way. Time may change, but we will assume that it's called a random access model. Okay. I mean, later on, we will using Turing machines or even circuits to define what is a formal algorithm or where what is a machine on which our algorithm is executing. For now, it is simply a random access model where you have an array where you can take your data, organize it the way you want, and just perform your operations and execute your algorithm step by step. Now, what is time, right? I want to mention typically we will assume addition of two numbers, multiplication, division, mod, comparison operation. I take these two numbers and I ask, these are all we assume can be done in constant time. So when I say time, I mean the number of steps, some constant 5, 10, 3, whatever, some constant number which doesn't depend on the input size, and that's how I'm going to measure my running time of the algorithm. Now, it may or may not be reasonable to assume this. For example, if you have two large numbers, it may be unreasonable to assume that you can do the multiplication in really same time as addition. We will get to that when we by and large we will not have large numbers. Okay, so typically we will be working with this reasonable assumption that all these operations can be done in constant time. Okay, and okay, now let me just introduce some notations. See, our purpose is to analyze algorithms in a machine independent way, in a programming language independent way. So that's using this pseudocode, which has a for loop, while loop. I'll use these if then else, and then I might say x is assigned some whatever is stored in this variable is copied into x. I might use repeat. These are some of the pseudocode, which typically what this means that you can convert it into any programming language of your choice. Okay, but now when I analyze these algorithms, I want to take into account that there may be some issues when you actually implement in different programming languages. There may be some things you can do faster. So there are two ways you might analyze algorithm. Like last time when we did, I might pick one operation, like let's say when we talked about binary search or merge sort, I will say I'm going to count how many comparisons are performed by the algorithm. That's clean. It doesn't talk anything about time really, but it just talks about zooming in on one operation and then I'm counting it. Okay, that's one way to do it. The other way is that I'm going to count all the steps together, but I want to take into account that some steps may actually take a different constant time than some other step. So we care only about asymptotically for large values of n, how much time it takes. So the operation the notation we will use is this big O or big theta. Okay, so again, have you seen this notation, big O? How many have seen this? A few. Okay, so So our algorithm's running time could be really, if I really want to care about the number of steps, time taken by the algorithm with all these assumptions, it may be 2n square plus 3n minus 5, right? Now, to me, that's sort of an n square algorithm, because as n increases, what really matters is the leading term, even ignoring the coefficient of the leading term. Okay, so we say a function f of n. Our functions are all going from natural numbers to natural numbers, because we will be working with data whose size is a natural number. This f of n refers to the time, the number of steps taken by the algorithm. So that will be a natural number. In fact, a non-negative natural number, and we say that f of n is big O of some other function g of n. Roughly, I want, what that means is f of n is upper bounded by, think of big O as something like an upper bound, okay, but I have some leeway. Okay, if there exists a constant c greater than 0 such that, so because I said I also want to go and ignore the leading term, right. So 2n square and 5n square and half n square are, to me, they are all the same. So if f of n is some upper bounded by some constant times g of n, and what else? People who have seen this. Sorry? Yes, exactly. If there exists c greater than 0 and an integer n such that for all n greater than or equal to capital N, which means that I care only about for large values of n, right, because your function so your c times g of n may be something like this, and my f of n may be like this, right. Sometimes it goes up above that, but after a point, after this n, my f of n is lower upper bounded by c times g of n. So, and the reason is that typically for small, so we will see examples. For small values of n, you may not want to do anything complicated, you may do something simple, right. So, if I want a good sorting algorithm, if I want to sort some 10 elements, you don't want to do recursion, divide and conquer and all that, because the extra overhead will eat up so much that it's not worth it. So typically for small values of n, you might do something simple. So when you do the running time in terms of the steps we have looked at, that may be actually more than the function you want to upper bound it by, but as n increases, it's upper bounded by c times g of n. Okay, so this is going to be, so it's easy to remember. Simply f of n is upper bounded by g of n. Okay, so now, so in that sense, the max finding algorithm we saw which I store the first element as a max and then have a for loop which compares every new element with this, and if it's larger, swap it. It's an order n algorithm because the total time taken is at most some constant times n. That constant actually is even 1. Okay, but it is also an order n power 100 algorithm, right? Yes, no? Yes, right, because it just fits the definition, because f of n is c times n power 100, because if it is less than or equal to c times n, it is also less than or equal to c times n power 100. So, somehow, so big O is not saying more precisely what I want, right. So, you need something else to tighten this. So what is the notation? So it's theta g of n if there exists c greater than 0 and let's even say c d greater than 0 and an integer n such that f of n is less than or equal to c times g of n, but greater than or equal to d times g of n for all n greater than or equal to capital N. Okay, so that means it's sort of upper bounded and lower bounded by g of n, right? Now, if you have only this, then there is a notation which is also used omega. If omega, so this is sort of a, you can think of it as less than or equal to, think of it as greater than or equal to, and think of this as equal to, right? Roughly speaking, okay, because it's not exactly that, because you have the constants playing a role, c, and there is a capital N playing a role, but so if there exists, right, so if fn is greater than or equal to d g of n for all n greater than or equal to n, then we say that fn is omega g of n, right? So let's see, I want to say 2n plus 3n square so is this correct? Right. So how do we prove this? I have to say that this is upper bounded by some c times n cubed for all n greater than or equal to capital N. So you have to come up with the c and the capital N. So what would be your c here? 1, because okay. So you want to say because 3n square plus 2n is less than or equal to n cubed for all n greater than or equal to, what do you want to say, capital N? 100, okay, fine, right. So, even 5 I might say, right, because n greater than or equal to 5, so 3n square is less than or equal to, okay, maybe 10 or something, because you will say 3n square is less than or equal to n cubed by 2 and 2n is less than or equal to n cubed by 2, so the sum is at most n cubed, okay. So can I say that this is omega n cubed? No. Let's try and see why not, right? I mean, so omega means greater than or equal to, right? So I have here. So suppose there exists. So let's try and see why this is not true, right? Suppose not. Suppose yes. Then there exists c greater than 0, capital N greater than or equal to 1, such that 2n plus 3n square is greater than or equal to c n cubed for all n greater than or equal to capital N. Okay. So what do you want to do? Okay. How do you get a contradiction? find the zeros, okay. So let's divide everything by n, right? For example, because n is positive number, which means that 2 plus 3n is greater than or equal to Cn square. Okay. And 2 plus 3n is greater than or equal to or less than or equal to, I might say, let's yeah, you want to say this is at most some 6n or something, right? Because n is greater than or equal to capital N, which this tells you that Cn is less than or equal to 6 for all n greater than or equal to capital N. So, n is at most 6 by C, which is not true, right. Okay, so I will set up some assignment where you get a feel and drill on how you would show or get a, I mean, if it's n square, n cubed, n power 4, you have an idea, but what about, let's say, n log n power 100 and n square. Okay, so which is big O of what? Okay. Right. So one suggestion is take log of both sides. So you will have log n plus 100 log n, whereas here you will get 2 log n. So if I knock off 1 log n, what I really care about is what can you say about 100 log n and log n, which is a fast growing function, right? So one way actually to see it, I mean, between log n and n, what is the no between log n and n, which is a fast growing function? N. So this is basically what log of something and something, right? Instead of n, you have log n here. So this will be the fast growing function. So this would be big O of that. Okay. So I'll set up some assignment where you get familiar with these notations. Let me also introduce a couple of more notation which is useful. So any questions, anything? Yeah, so it's important to get the hang of, so for example, what about 2 power n and 3 power n? Clearly this is bigger, so you might say this is big O of that, but is the reverse direction also true? So 2 power n is big O of 3 power n, right? That everybody would say, because 2 power n is less than or equal to even 3 power n for all n greater than or equal to 1 or something. You can easily say. So this is fine. What about this? Yes? No? No. Yes? It is? Yeah, but okay, so one suggestion is if you take the log both sides, they are of the same asymptotics, okay, because this is n log 3, this is n log 2, log 3, log 2s are constant, they are the same. But on the log, yes, but sorry? Yeah, exactly. So what he's saying is, in that case, even n cubed is big O of n square, because take log, it will be 3 log n, that will be 2 log n. We know that's not true, right? So how would you show? Let's try and show it is, okay, and then see what the problem is. That's all. There is very easy to figure out. Okay, so that this implies what? There exists a C and an N such that 3 power n is less than or equal to C times 2 power n for all n greater than or equal to capital N, right? Which means what? This implies 3 by 2 whole power n is less than or equal to C for all n greater than or equal to capital N. This is obviously not possible, right? C is a constant, whereas this is a growing function of n, right? This is a contradiction. So, couple of more notations, right? So, let's say I want to say big O, big little o. Okay, so this is what does little o means? Basically, it has a flavor of strictly less than. Okay, so if I say this is less than, this is like a strictly less than. So, what does that mean? Um, so, Fn is little o of g of n means that Fn is less than Gn or C times Gn for all C greater than 0. So, this is not there exists. You tell me any C, Fn will be less than G of n, C times G of n. An equivalent definition which many of you can easily relate to, um, you could say that, but doesn't matter really, because an equivalent definition is this, that Fn by Gn, what do you think? Fn is a strictly slow growing function than G of n. So, this limit will be so as n tends to infinity, since Fn is a strictly slow growing function than G of n, this is going fast. So, what would be the limit? 0. Yes. Right. So, for example, what would this be if Fn is theta G of n? If Fn is theta G of n, then the limit would be constant, right? So let's look at some example, right? So what can you give me a function which is little of n? An example? A strictly slow growing function than n. A constant, yes, yes. What did you say? No, I'm talking. I want a function which is little of n. Yes. Okay. N and n square is fine. So what? N is little of n square. Yes. Sure. But what about constant? Some other function? Log n, square root of n by log n, right? N by log n power 100. Because limit n tends to infinity fn by gn would be this n will cancel out and it will be 1 by log n power 100. As n tends to infinity, this will go to 0. So strictly smaller than is what is little o, and in the same fashion we have an inverse thing which is little omega, right? Omega, which means that strictly bigger. Okay. So for example, n square is strictly bigger than n. So here is a now that I've introduced this little o, let me give an exercise. So we talked about finding the maximum, right? What about finding the second maximum? Okay, finding max, remember the algorithm was I take the first element and I had a for loop. And this is the finding max algorithm which took n minus 1 comparisons because you are doing some n minus 1. Okay. N minus 1 comparisons, maybe in the worst case even n minus 1 of these assignment statements plus this assignment statement. If I want to find the second max, what would be an algorithm to do it?
Like find the max, I'm storing it
Okay.
a variable, and then again apply the find max.
Okay.
I don't swear if I get that right.
Okay. So my goal is finding second max. The suggestion was find max, somehow delete it, right? And then find max again. So how many comparisons would you have taken so far? N minus 1 plus n minus 2, right? Okay. So here is an exercise. Find second max using n plus little of n comparisons. Okay, because this 2n minus 3 is n plus n minus 3, which is not little of n. Is that clear? Not. This is what little o means. If you put n minus 3 and n here, the limit is not 0. So n minus 3. So when I say less than, in the asymptotics, remember when I say less than or equal to or greater than or equal to, don't take it literally, right? With all the constants and for all n greater than or equal to n, all that similarly. So even though n minus 3 is less than n, n minus 3 by n limit, what is it? What is the limit of n minus 3 by n? 1. It is not 0. So, n minus 3 is not a strictly slower growing function than n. So, I am asking for an algorithm where the leading term has 1 n and the remaining should be a little over n number of comparisons. Yeah, array of n elements is given. You are given an array of n elements. Come up with an algorithm to find the second max. Yes? Yeah, we are counting only comparisons. Yeah. Okay. Okay. Yes. Okay. So, okay, I think I understand what you're trying to do. So let me write down and tell me whether that's correct. And this is what you had in mind. So we'll store two variables, right? Instead of max, I'm going to store two variables. Store the first two elements, and my algorithm now will go from 3 to n. So tell me what I should do. If ai is greater than max, then max would be ai. Else, if ai is greater than second max, then second max would be ai. Else, don't do anything. Okay, is that what the algorithm you had in mind? You're storing two elements, maintaining two elements, and running through a loop, comparing with each one and see updating it. Yeah. Oh, sorry. Okay. Yes. Okay, so if ai is greater than max, then max would be ai and S max would be max, correct? Right?
So first you need to assign S max will be max, then max will be.
Yeah, sure. Thank you. That's a very good point, right? Why? How does it matter? Why?
Or else the value of that max will be changed. So both will continue.
Yes. So I store max and second max. I compare it with this. If the element I am bringing in is larger than this, that guy will occupy this and this will go here. But I have to do, S max gets the value of max and max gets the value of ai. Suppose not, suppose that is smaller, then I compare it with S max, and if it is larger, then the S max will be occupied by ai. Right? First of all, is this fine? The initialization, is it correct?
Actually, we start with, first we are starting with the max ai, but when we are shifting the max, then we assign a value to S max. When the first we are assigning a1 to max, and then we are comparing with a1 with a2, a1 with a3. Now suppose at a condition when a1 is.
Okay, so you're saying basically don't do this. And we'll see. Yes? But then I can't do this comparison because if
We need to, because when I am swapping with the max.
No, this is an else. If ai is smaller than max, first time maybe you store it as a S max maybe. Yeah, exactly. So okay. So I know, good. It throws in a lot of things, right? Correct. We are talking about an efficient algorithm. Let's make sure it's correct first, right? So here is a suggestion. If A1 is greater than A2, then max is A1, S max is A2, else max would be A2 and S max would be A1. Then you run this from 3 to n. So take the first two elements, store. So now I can prove what this algorithm is correct, because what is the invariant we are maintaining? I mentioned about invariant, right? What is the invariant? The max will be the max element, the second max will be the second max element at any point of time, right? When I say any point of time, at any value of I. If you stop your loop at some location, some index I, and look at your max and second max, you will actually have your max and second max up to that point, which you can prove by induction, because this is the base case. Assume it is true, then you can prove the induction step. So all that is fine. How many comparisons does this algorithm make in the worst case? So here there is one comparison, and here two into n minus 2, right? Because 3 to n is n minus 2. So 2 into n minus 2. So this is like 2n minus 3. Not such a big improvement from what we had before. So in particular, 2n minus
3 or we had 10 minutes.
Yeah. So in particular, this is not n plus little of n, right? Okay. So think of an algorithm which will find the second max. So, I mean, if you go back to the knockout tournament way of finding the max, typically we will declare the loser of the finals as the second max, right? When you run a knockout tournament, it may or may not be really, right? You can come up with examples where if you do this pairwise games, knock people out as and when they lose and do the finals, and look at the loser of the final, you can't declare it as a second max. So come up with an example where that will not be second max, and then that will give you an idea of how to find the second max in a few more comparisons. Exactly. So yeah, so the hint is the tournament way of finding max. Okay, use this is another max finding algorithm. Last time we pair people, the winners move up to the next round, and then we did some analysis and found out that this also takes n minus 1 comparisons to find the max. Now, how much more do you need to find the second max? Okay, so I'll leave it at that. You can think about it. We'll get to it next time. So now, let's get back to merge sort, which was the algorithm which I described towards the end of the last lecture, to sort n numbers, right? So recall the algorithm was sort the first half of the array recursively. So this recursively is another programming terminology, is very useful, which is basically an algorithm calling itself on an input of smaller size. Okay. So at the end of these two steps, you have the first half sorted, the second half sorted. So this is like, so each of this is sorted. Now to complete the entire sort, you have to merge these two sorted arrays, and so that is an external routine. It's not a recursive. So how do we merge two arrays which are individually sorted? We went through this last time. Let me see if I can actually write the pseudocode, right? I'm not going to do write pseudocodes very often, but this is the beginning set of lectures, so let me write. So you have an array of n elements and an array B of m elements, individually sorted, right? And you want to merge them. So I keep saying elements. So these elements are, you can think of them as numbers, but typically they are a set of objects from any totally ordered set, right? Because we really be able to compare any pair of them and know whether it is smaller or bigger or equal. That's all. So it could be characters, strings, whatever, but let's say some numbers, okay? And anyway, comparison takes constant time in our assumption. And I want to output in this big array C. So let's use an external array which has m plus n elements. So how does the algorithm work? We are going to compare the first two elements, first element of A, first element of B, whichever is smaller will get output here, and then you move the pointer. And so what would be a way to write a program? So here it is, right? So I equal to 1, j is 1 and k is 1. So think of I running on this, j running on this, and k is running on this, right? Okay, so if ai is less than or equal to bj, then yes, then C. Hmm.
Let us say k equals to bj, then increase pointer of j from I.
Then ck is ai, and I is incremented, right? I move the pointer. Else ck is bj, j is incremented, and k should also be incremented, whatever, right? Either case, k has to be incremented. How long does this go on? What sort of a loop do you want?
Whenever I or j is I less than I m.
Yes, so I'm going to say while I less than or equal to n and j less than or equal to m.
Then k equals to k plus 1 will be bigger. Increment.
Yeah, after this if then else it has to be incremented. Yeah, not individually, but this is outside. Yeah, is that all? There's a little bit more to do.
And then whether remains the remaining part is there.
Yes. So when do you get out of the while loop? Well, maybe I has reached n or j has reached m. So you actually I has shot to n plus 1 or j has gone to m plus 1. Then you will come out, right? Come out and then do what? So, so copy the remaining elements whichever is not reached into C, right? So there will be a, you know, so if I is n plus 1, then for j or L equal to j plus 1 to m, Ck is Bl and k is going to k plus 1. Else if j is n plus 1, do something similar. Basically, if I has reached n plus 1, then whatever j is sitting there, copy all these guys and put it in the remaining C. If j has reached n plus 1, whatever remaining and put it in C. Okay, so you get the idea, you need to fill it up. So the correctness is important, make sure the boundary conditions are all right. So that's the merge algorithm. Now let's for now again count only the number of comparisons. Okay. So how many comparisons does this algorithm perform? Right. So this is where, so this is one comparison, right?
N plus m is the bound.
Yes. So in the worst case, after every comparison, either I or j moves. Right. So if you look at the movement distance of I and j, totally it's m plus n. Right. So it's actually m plus n minus 1 because one of them would have finished before the other guy and you might get the last element for free. Okay. So at most m plus n minus 1, but it's okay if we just say m plus n comparisons. Okay. So this is the merge routine. So now let's come back to the merge sort and see how to analyze the number of, again let's count the number of comparisons. Okay. So this, how many comparisons are performed in this merge routine? The third step is an external routine, right? So this algorithm. What is m? What is n? In this case.
Length of the arrays.
Yeah, I told you what the length is, right? We are talking about totally n. N by 2 plus n by 2, right? So this is n. So number of comparisons made in the last step is n comparisons. Okay. So the algorithm is clear that it will sort the first half, calling the same algorithm again and again repeatedly. The good thing is you don't have to worry about the implementation. The operating system takes care of it. Okay. So actually, what will it do? How will it sort the first half? It will divide it into a quarter, first quarter and the second quarter. Sort the first quarter, sort the second quarter, and merge. Merge is the external routine. How will it sort the first quarter? We will divide it into 1/8 and second eighth. So all that. So it's a very compact. When you write a program, this is the entire algorithm. Right? It's a very simple code. So now how many comparisons are performed in the first step?
By sorting first.
Yeah. So we want to analyze this algorithm. We want to count the number of comparisons performed in each of the steps. In this step, there are n comparisons. How many comparisons in the first half to sort the first half?
In total time to sort it is
Yes, exactly.
I mean,
Not n by 2.
sort the entire array.
The size of the array is n by 2. I am asking how many comparisons are made to sort the first half. Any ideas? See, it's a very loaded statement, right? Because the algorithm is calling itself and calling some merge routine and again and again. Yes? N by 2 power? N by 2 for large n. Ah, I see. Okay. That is the number of comparisons performed. Why? I mean, it's not clear, right? It is recursively sorting it, right? Yes. So the third step in the first recursion. Yes. We take n by 2 comparisons. But to sort it again, each of the two halves will take n by 4 comparisons. Yes. So there are several n by 2s happening, right? So, okay. So let's see it as a, okay, one way to see this is draw what is called a recursion tree. Right. So what will happen is the third step takes n comparisons to merge, and then you are sorting some n by 2 elements and sorting n by 2. Well, the third step for this will take n by 2 comparisons, and then it will have, so this will also have an n by 2, and then you are sorting some n by 4 and n by 4. The third step here will take n by 4 and n by 4, but then it is broken into the n by 8, n by 8. So for now, let's assume all these numbers are integer, right? So n is a power of 2, because otherwise n by 4, n by 8, they may not be integers. So let's assume that you can divide n by 2 power anything. So n is a power of 2, right? And so on and so forth, right? So there will be n comparisons at the last step, but before that you have to sort n by 2 and sort n by 2 elements. For that, the last step of that will take n by 2 comparisons, last step of that will take n by 2 comparisons, and then you have to sort n by 4 and sort n by 4. The last step will take n by 4, n by 4, n by 4, and so on and so forth. Where does it end? Yes, when you have one element or two elements, something. So one of the things you need is a bailout condition, right? For any recursive algorithm, it's like a base case of induction. You need to be able to get out of the recursion at some point. So you can say, either you can say if n equal to 1, then output the element. So you're done. You don't need to do any recursion, no comparison. Or you can say if n equal to 2, then sort of if a1 is greater than a2, output a2 a1, else output a1 a2, which means that I am doing these steps only if n is greater than 2 or 1, whatever, depending on your n condition, right? So the whole algorithm will stop if there are one element here. Okay. So what would be the total number of comparisons? Well, there are n comparisons at this level, n comparisons at this level, n comparisons at this level, and how many levels are there? K many levels if n is a power of 2, because when you reach here it will be n by 2 power k, and that's when you don't do any comparison. So at this point you don't do any comparison, but up to k minus 1 starting from 0. So that will be n times k comparisons. But k is log n here because n is 2 power k. Okay. This is one way of analyzing the algorithm. So, sort of write a recursion tree. But there is a very even simpler way, and that is, say, suppose I don't know what the total number of comparisons made by this algorithm is, but let us call it by a function T of n. Okay. Okay, you will see again. For now, we are going to assume n is the power of 2, and later I will deal with the case what if n is not. So, suppose I say the total in the worst case. Why is it worst case? Because this is worst case n comparisons. Remember, for merging, there are times where maybe n by 2 comparisons are enough, because if the first array has run out, that's the number of comparisons we made. So, here is a key thing we are looking at in the worst case. Okay. So, if Tn is the total number of comparisons made by the algorithm in the worst case, how many comparisons are made in the first step? No. To sort by this algorithm will take at most T of n comparisons. Okay. T of n by 2, exactly, right? Because now that I have defined this function, I can write this functional equation. So, the number of comparisons made here, I don't know what that is, but as a function, it's T of n by 2, because I am applying my original sorting algorithm on a list of size n by 2. So, whatever that was taking on list of size n, it will take an appropriate thing for T of n by 2. So, this is T of n by 2, this is another T of n by 2. This I know is not a recursive step, this is an external algorithm. So, this overall thing would be 2 times T of n by 2 plus n. Okay. And this is 1 if n equal to 2. So, you need a boundary condition, because it is an equation you want to solve this. Okay, or maybe I will say 0 if n is 1. All right. Because when I come to one element, I have nothing to do, no more comparisons, I can just output it. Okay. So, recursive algorithms are analyzed using recurrence relation. So, this is a recurrent, this is called a recurrence relation. Now, we need to solve this. Okay. Let us write a recurrence relation for binary search we saw. What would be if T of n, this is for merge sort. If T of n is the total number of comparisons made to search in my sorted list, can you give me the recurrence relation for T of n? How many comparisons I am performing, right? So, what is the first step of binary search? Compare it with the middle element, right? So because basically what is binary search? You can say 1 to n would be if my element x is less than or equal to, let us say it's a n by 2, then search in 1 to n by 2, else search in n by 2 plus 1 to n. So, that is my binary search, right. So, how many comparisons are made? Can you, because it is a recursive call, I am going to write a recurrence relation. So, what is T of n? How many comparisons? So, where is the comparison happening? Here. So, 1 plus T of n by 2. That's it. That's a recurrence relation, right? And if n equal to 1, then T of n will be 1, because I am just going to take my x and compare it with that one element and answer if it is the same as x, otherwise, I say x is not present. Okay. So, recursive algorithms are very nice, you can write compactly, and the way to analyze recursive algorithms is by using what is called a recurrence relation. Okay. The next question is, how do we solve this recurrence relation? So, let me give you a flavor of the solution, at least when n is a power of 2, right, for both. Then we will get to more formal way of analyzing or solving this recurrence relation. So, the idea is to just keep expanding, right. So, again, let us say n is 2 power k. Let us look at binary search. T of n is 1 plus T of n by 2. Well, what is T of n by 2? Just bootstrap in the same equation, it will be 1 plus T of n by 4. This will be 1 plus 1 plus 1 plus T of n by 8. So, dot dot dot, what do I get? It will be k plus T of n by 2 power k. Since n is 2 power k, this will be 1, and T of 1 is 1 because I am making 1 comparisons. So, this will be k plus 1. This is one way to solve it. I mean, a more formal way is to use this idea to guess your solution and prove it by induction, right. You can now plug it in and prove by induction that for n equal to 2 power k, it is k plus 1. Why? Because of how do you prove it by induction? Base case T of 1 is 1, because it's 1 is 2 power 0. Assume it for induction step for all values up to n. So, T of n is 1 plus T of n by 2. So, for n by 2, it will be k minus 1 plus 1. So, everything will cancel out and it will be k plus 1. See, so this dot 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 is not a formal proof, but this you use it to guess the solution and then you can prove by induction. Okay. I still have to deal with the case, what if n is not a power of 2? Well, we will come to that next time, but let us do something for merge sort. Where you have T of 1 is 0, because if there is one element, you do not need to do anything to sort that element, right. So, you can write this as T of n is n plus 2 times T of n by 2. And I expand it, I get, what is T of n by 2? N by 2 plus 2 times T of n by 4. So, this is n plus 2 square times T of n by 4. Right. So, if I do one more time, n plus 2 square into n by 4 plus 2 times n by 8. So, this will be n plus 2 cubed into T of n by 8. So, if I will have k n plus 2 power k into T of n by 2 power k. T of n by 2 power k is 1, T of 1 is 0. So, this whole thing will go away. So, it will be k n, and k, remember, it is log n to the base 2. So, it will be an n log n number of comparisons, and the other operation, number of moves, will also be n log n, because the entire load is in the merge routine, right. And the merge, apart from making n minus 1 or m plus n minus 1 comparisons, it also performs m plus n minus 1 moves. Of course, one problem with merge sort is it requires this huge extra space to do this merging. Okay, so something in keep in mind, but we have the first, at least you have seen, an n log n sorting algorithm which performs n log n comparisons, n log n moves, n log n everything else as well. Okay, improving from n square, which is very useful because first time when we started, we said for the value of n we are dealing with n square and n log n. There was a contrast of 40 seconds. Okay, so now next time we will get back to what if n is not a power of 2 and how do we solve in general these kind of recurrence relations. Right? So again, this dot 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 is not a proof, but if you guess this, derive this from this, now you can plug it in and prove by induction. Right? Because when k is 0, this will be 0. So when n is 1, and assume it is true for smaller values of n, then it will be 2 times k minus 1 plus 1. So this will be 2k. No, sorry, plus n, right, 2 times k minus 1 times n plus n. So this will be 2k. So my claim is it's nk. So it will be, sorry, not n by 2, right, n by 2 into k minus 1 plus n by 2, and the power of 2 in n by 2 is k minus 1. So this will be n into k minus 1 plus n, this will be nk. Okay, I am trying to prove by induction that the solution to this is nk. Right. So by induction, here this will be n by 2 into k minus 1, because the number, because n by 2 is 2 power k minus 1. So n by 2 into k minus 1 into 2 plus n, this 2 and this 2 will cancel out. It's n into k minus 1 plus n, so that's nk. Okay, so next time we will look at more, how do we solve the recurrence relations in general, and look at more algorithms using this technique of divide and conquer.